Hello everyone and welcome to this presentation on the multiphysical simulation of ocean engineering systems. I am not aware how familiar you are with the topic of modeling and simulation, so we will begin the presentation by looking at some background information that will enable you to appreciate the subject matter in the subsequent slides. We will then proceed to discussions on modeling and ocean engineering system using the Modelica ocean engineering library. And we will then look at Cosimulation methodologies for linking ocean engineering software with other multiphysics software. And finally, we'll draw our conclusions. So when I talk about simulation in this presentation, I'm usually referring to calculations run on a computer to determine the behavior of a mathematical model. And by a mathematical model, I mean an abstract model that uses mathematical language to describe the physics that governs the response of the system. By abstract, I mean something that exists in thought or as an idea, in this case as lines of code. And this abstract model cannot be felt, but you can interact with it by giving in some input and analyzing the output. Now, if the mathematical model takes into consideration physics from multiple domains, then we refer to the simulation as multiphysical simulation. System, in this case a catenary moved buoy, to describe the interaction of the mooring chain with the seabed, we physical laws from the domain of soil mechanics. To describe the wave body interaction, we use hydrodynamics, and since this is a multi-body system, there is clearly influence from the domain of applied mechanics. So we conclude that even the simplest ocean engineering system is multiphysical. Now let's consider a barge floating on calm water at equilibrium. In this case, the weight of the barge is matched exactly by the buoyancy and the barge is at rest. Now let's apply a force F in the downward direction. Since the buoyancy is now overcome by the sum total of the downward forces, the barge will start moving down. And as it moves down, the submerged volume increases, the buoyancy increases, and there will reach a point where the buoyancy exactly matches the total downward forces. But the motion of the barge does not stop at that point, because as the barge starts moving down, there is a velocity and an acceleration associated with the motion, and hence there is inertia in the downward direction. And so the barge will move past the equilibrium point and come to rest as buoyancy overcomes this inertia. At this point, buoyancy exceeds the total downward forces and the barge will start moving up. Again, it will overshoot the equilibrium position by a slightly lower amount. It will come down again, and this process continues until the motion decays and the barge finally comes to rest at the new equilibrium position. Now, if we analyze the response, we see that the amplitude of oscillation is reducing, and this points to the fact that energy is being carried away from the system. Now, what causes this? As the barge moves, ripples are created on the surface of water, much similar to the case where you throw a stone into a pond and you observe the ripples. These are radiating waves. They travel away from the point of impact. In a similar way, these ripples travel away from the system under consideration, and this is the physical manifestation of the process by which energy is being transported away from the system. We see that as the barge moves down, it pushes water away from beneath it, and as this flow leaves the surface, there is flow separation and eddies are formed, and this causes the energy to be dissipated in the form of heat to the surroundings. And these are the two phenomena by which energy is transported away from the system and the amplitude of this oscillation decreases. Now, if we endeavor to write the equation of motion for this system, again Newton's second law, force is mass times acceleration. So the downward force F minus the hydrostatic stiffness acting vertically upwards minus the damping forces which take away energy from the system. This is equals to the mass times acceleration. So in this case, the stiffness is given by rho g AWP, where AWP is the water plane area. The damping coefficient has the contributions from the wave radiation damping as well as the viscous damping. And the mass in this case has two components: the mass of the body plus the added mass, which you can at this point understand to be the mass of water that is accelerated by the body. And so rearranging the terms, we come to an equation of the form, which I'm sure students of the higher semesters will immediately identify to be associated with a single degree of freedom spring mass damper system, which has a response similar to the one shown in the graph. Now let's look at a sample case where our objective is to determine the dynamic response of this catenary moved vessel with a crane carrying a suspended subsea load. We have information regarding the environment, the hydrodynamic particulars of the ship, data regarding the crane and the subsea load, as well as mooring line data. What we are basically trying to do is solve an equation of motion of the form that appear on the screen right now, which is analogous to the equation of motion that we described earlier. And in this case, the added mass is frequency dependent, the wave radiation damping is frequency dependent, and the wave loads are also frequency dependent. To determine these frequency dependent terms, we need to carry out something called as frequency domain hydrodynamic analysis. And to understand that, we need to look at the wave body interaction problem. So assume a body that is floating in calm water. As an incident wave interacts with the body, three things happen. A part of the incident wave is reflected as scattered waves. And since the incident wave changes the pressure distribution in the submerged surface of the body begins to respond. And as the body moves, radiation waves are generated. So if we assume linearity, that means if we assume that the motion of the platform is linearly proportional to the incident wave load, then we can split the problem into two. One is the diffraction problem, where we assume that the object is held fixed at its equilibrium position and the incident wave is acting on the object. And the other is the radiation problem, where we assume that the object is initially floating in calm water, and then we begin to oscillate the object in its 6 degrees of freedom, which in turn creates 6 patterns of radiation waves associated with each degree of freedom, and this is called as the radiation. The diffraction problem gives what is known as the wave excitation loads, which has two components. If we consider the unsteady pressure field due to the incident wave, this is called as the Fruit-Krylov load, and the hydrodynamic load due to the scattering of the waves is referred to as the diffraction load. The wave radiation loads consists of the added mass, which is defined as the hydrodynamic load in phase with the acceleration of the body, and the wave radiation damping, which is defined as the hydrodynamic load in phase with the velocity of the body as it is oscillated in calm water. Now for smaller objects, you can ignore the effects of diffraction because the object is small, and so the ability of the object to scatter the waves is small. And we can also neglect the effects of damping because the wave making ability of the object is small. Now, if there is significant inertia in the wave load, then the wave loads can be approximated as the Fruit-Krylov loads. And if there is significant drag when compared to inertia, then the wave loads can be prescribed by using the Morrison equation. In practice, the frequency domain hydrodynamic analysis is carried out using software like VAMET and ANSYS Aqua, which use the panel method. So in the panel method, the body surface is first modeled. It is split at the waterline. The center of gravity and the moment of inertia are specified. The object is discretized into panel. The surface is discretized into panel. And the wave directions and frequencies are specified, and the analysis is carried out. The output of such analysis is the frequency dependent added mass, the frequency dependent damping, frequency dependent Fruit-Krylov forces, frequency dependent diffraction forces, the displacement response amplitude operators, and the load response amplitude operators. The displacement RAOs give the response of a body in relation to a wave of unit amplitude, while the load RAOs gives the load acting on the submerged surface of the body associated with a wave of unit amplitude of a particular frequency. Once you have the displacement RAOs, we can simulate the vessel motion directly by multiplying the sea surface elevation with the response amplitude operator. This is done in cases where, for example, the suspended mass is less than 1 to 2% of the vessel displacement. And in this case, the dynamics of the mass does not significantly impact the dynamics of the vessel itself. However, in a case where the suspended mass is, for example, greater than 1 to 2% of the vessel displacement, or if you want to take into consideration the effect of the mooring lines, then you have to use the load RAO option. In this case, the equation of motion is solved with the load RAO multiplied with the sea surface elevation to give the wave load. But the solution of equations in this form is not straightforward because this is a time domain equation with frequency domain components. So these frequency domain components have to be made suitable for use in time domain equations. And for that, we use convolution, where convolution in this case can be understood to be the summation of the impulse responses. So if we want to analyze the response of a system to a load that varies as shown by the blue line in this graph, then we discretize that load into a series of impulse loads, and then we calculate the response of the system, the impulse response of the system to each of these loads with 0 initial conditions. So for example, for the first load, the response is shown by the yellow line. For the second load, the second impulse load, it's given by the magenta line, and so on. So if we want to calculate the response of the system at, say, time equal to 8 seconds, then we sum up the responses of the individual impulses, and that gives the response of the system at the 8th second. Now this was suggested, the concept was suggested by Cummins in 1962, and in the paper by Vichers in 1979, they implement this method, where they calculate the vessel impulse response function and apply the impulse response function at each time step using a convolution integral to account for the past motion of the vessel. So, in order to solve equations of this form, for example, we in OrcaFlex, these black equations are from the manual of OrcaFlex. So here, the added mass and damping loads in the frequency domain are expressed in the time domain by this equation, where A infinity refers to the infinite added mass and the IRF refers to the impulse response function. To calculate the infinite added mass, you need the added mass metrics at different frequencies. And to calculate the impulse response function, you need the radiation damping at different frequencies. And this is why you need to actually import the frequency domain hydrodynamic data into time domain software like OrcaFlex. So let's look at an OrcaFlex simulation now for the case that we are considering. So the simulation is in progress. So here I have previously carried out the frequency domain analysis for the same vessel in ANSYS Aqua and imported that data into OrcaFlex. And then I have attached mooring lines and the subsea loads inside OrcaFlex, and all these are basically Morrison elements. And this is how the simulation progresses. But what if you were interested in the dynamic response of the systems of the crane and not actually on the dynamics of the vessel? Well, in that case, the crane has components from the mechanical, electrical, electronics, and hydraulic domains.
and Orcaflex does not have component models to model these parts. So we will have to resort to the use of languages like Modelica, which are specially written to model multiphysical systems. And so Modelica is a non-proprietary, object-oriented, declarative, multi-domain modeling language for dynamic simulation. It uses the causal modeling philosophy, which means that you are solving equations and not assignment statements. So you can have knowns and unknowns on either side of the equation, and then the solution direction depends on what is required. It is extensively used in the aerospace and automotive sectors, and it has a standard library with many components from almost all domains of engineering. There is one open source distribution of Modelica, and that's Open Modelica, and OM-Edit is its graphics user interface. The figure shown is the standard library of Open Modelica. There are many commercial distributions like Demola, Simulation X, MapleSim, and Modelon. Now, what are the limitations of the conventional ocean engineering and conventional Modelica software? Well, the ocean engineering software lacks component models to model multiphysical systems. And the multiphysics software like Modelica, they do not have a hydrodynamics library. And so it's quite hard to model ocean engineering systems using only multiphysics software. So what's the solution to this? For the lack of multiphysics components in the ocean engineering software, you can develop cosimulation methodologies to link ocean engineering software with multiphysics software and then carry out multiphysical simulations. For the other case, where there is a lack of ocean engineering library in the multiphysics software, since Modelica, the language itself is open source, you can develop component models for the ocean engineering domain. So that brings us to the Modelica Ocean Engineering Library, where we try to develop a library of component models for ocean engineering systems. So this would require, for example, simulating systems like a catenary moved buoy, where the wave forces on the buoy as well as the mooring line are to be calculated. Or maybe you want to calculate the wave forces at fixed structures like a monopile, or the structure could be free floating like a ship. So what is common in all these models is the environmental parameters are common, but you need to calculate the loads only at specified locations. So what we propose is the development of component models for waves and currents and other environmental data like wind, stuff like that. And once the parameters are generated, they are fed into a database. And from this database, the individual component models then make use of this data to calculate the, for example, the wave forces on the buoy or on the mooring line. Look at the development of component models, and the first one is the regular wave. The velocity potential for the regular wave is found out by solving the boundary value problem. And once the velocity potential is known, analytical expressions for all the other wave properties can be obtained. We implement these analytical expressions inside the component model for regular waves, and we provide some verification of the results. When it comes to the irregular waves, we use the concept of the wave spectrum and the Fourier series decomposition of the irregular sea surface into component waves. And we develop a component model where we can specify the wave spectrum, and by assuming random phase, we then generate the irregular sea surface elevation. When it comes to component models for current, it's more straightforward. We can specify the current at different depths along the water column, and for intermediate points, then the value can be calculated using interpolation. In our case, we use linear interpolation. In all the wave and the current component models, we also give the functionality for ramping up the loads, so as to prevent shock loading of the system when you are using it in an integrated simulation scenario. In developing the component models for non-diffracting floating objects, which means that the object is relatively small compared to the wavelength. We use the simplifications that we described earlier, the Fruit-Krylov load and the Morrison load. And again, we compare our results with the results obtained using Orcaflex, and we demonstrate satisfactory agreement. In developing the component model for catenary moorings, we use the quasi-static catenary theory, where we basically derive the relationship between the horizontal tension and the x position of the top end of the catenary with respect to the anchor point. And we use the Morrison equations again to determine the fluid loads on the mooring line itself. We compare our results with results obtained using Orcaflex. And so we now have developed component models for the waves, the currents, for fluid loads on the buoy, as well as component models for the mooring loads. And so we implement that in an integrated simulation where the component models for the waves and the current, they generate the parameters, feed it into an environment bus, from which the buoy and the mooring component models take these parameters and calculate the fluid loads. And we then compare the response of the integrated system with a similar model in Orcaflex, and we see that there is satisfactory agreement. So the development of the component models are dealt with in detail in two publications, which were presented at the Modelica conference in 2020. In another work, we present how the ocean engineering library can be used to, for example, determine the dynamic response of a spring suspended mass inside the buoy. This is done by extending the integrated model that we described earlier with component models already available in the Modelica standard library. Again, we present results by comparing the Modelica results with Orcaflex results. This is done for a slightly different configuration of the system also, where we use a rectangular pontoon instead of a buoy. When it comes to the utilization of the ocean engineering library, we came across a recent publication from the researchers at Manhattan College in New York, where they use our ocean engineering library. They extend it by using other component models to arrive at a design of a wave energy converter buoy, which can be used in navigational signaling. They develop the model and they test it in a wave tank and ascertain its satisfactory performance. In extending the ocean engineering library, we have presented a work where we use the lumped mass approach to the mooring catenary. In this case, the catenary line is discretized into lumped mass points, and we use the quasi-static catenary theory for the initial configuration of the catenary, and from that point onwards, it is the lumped mass model which is used to calculate the dynamics of the mooring line. This was presented along with implementation codes in both Modelica and in Python, and we compare the results of the model with the results obtained using Orcaflex, and we see satisfactory agreement. There are many shortcomings. However, all the results are presented in a paper along with the Python and Modelica codes. And in another publication, we present the results for the dynamic simulation of a chain suspended subsea load, where again we use the lumped mass approach. But in this case, we modify the components already available in the standard Modelica library to build up the model of the chain suspended subsea load. And we make use of drag and buoyancy blocks, inside which we use the Morrison equation to calculate the fluid loads. And it's seen that the results using this method is more in agreement with the Orcaflex results. And the Modelica code is available for reference, and the download location is given in this paper. In order to extend the ocean engineering library by including component models to simulate for the hydrodynamic response of larger diffracting objects, we need to solve the wave structure interaction problem in its entirety. That means we have to solve the diffraction problem to determine the wave excitation loads and the radiation problem to determine the added mass and damping loads. And to solve this wave body interaction problem, we need to represent the presence of the body mathematically in a flow domain. And we do that by adopting the method used by Sir Horace Lamb, where he uses sources distributed on the body surface and the concept of the green function to mathematically represent the presence of this body. And in this case, since we have waves, the green function will have a steady part and an unsteady part. In evaluating the wavy part of the green function and its derivatives, we use the Fortran code, which is provided by Teleste and Noblesse in their paper published in 1986. And to evaluate the steady part of the green function, we use the Hess and Smith panel method, where the body surface is discretized into panels of constant source density. Hess and Smith also gives analytical expressions for the integral of the green function and for the integral of the derivatives of the green function at a field point due to source distributions on the panel. And so we now have ways to determine both the wavy part as well as the steady part of the green function. And once we have that, we can formulate an algorithm to solve the diffraction radiation problem. This is done using Python, where the wavy part of the green function is determined by a Fortran code wrapped for Python using the F2Py interface. The Python code is open source and it's named OMHide. Using OMHide, we can visualize concepts like what happens if you place an object in a flow domain. For example, if you place a cuboidal object in a uniform flow domain, as the flow approaches the object, it starts diverging, and as it leaves the object, it starts converging. This shows the water particle velocities in the Z plane. Again, you can visualize what happens if there is a free surface present. And in the case of a free surface, you need to specify an image body to actually account for the flow. It can also visualize radiation waves. For example, this graph shows the radiation waves associated with the surge of a floating object. So as the object surges forward, you can see that the water particles have a velocity that point to water being pushed in front of the object while being pulled at the back of the object. This shows the water particle velocities in the Z plane. You can also do panel convergence studies and other stuff. But the main point is that you can calculate the added mass and the damping as well as the excitation loads. And these are basically the frequency dependent parameters that you need in order to carry out a time domain simulation of larger diffracting objects. The entire code is open source, and it is described, the working of the code is described in a paper which has been published in the MIG journal. We will now proceed to discussions on the cosimulation methodology, and we begin by looking at the offshore load handling system. Load handling is one of the most frequently carried out operations in the offshore environment. The loads can vary from very light loads to very heavy loads. Usually, the lifting operation is classified into two: a light lift, where the load to be handled is less than 1 to 2% of the vessel displacement, and the dynamics of the load in this case has no significant impact on the dynamics of the vessel, and so you can use the displacement RAO option to specify the platform motion. But in a heavy lift, the load to be handled has a mass greater than 1 to 2% of the vessel displacement. And the dynamics of the load has a significant impact on the dynamics of the vessel. And so you will have to use the load RIOs to determine platform motion. So in the Cosimulation methodology, we model, for example, the electrohydraulic drive of the winch in a Modelica software called Simulation X, while the vessel and the suspended load is modeled in Orcaflex, and then we use an API interface to connect both these subsystems. This figure shows the electrohydraulic drive of the winch modeled in Simulation X. Simulation X has component models to model the hydraulic motor and the hydraulic valves, as well as the pulley and the belt arrangement for the winch wire. While this figure shows the vessel and the subsea load modeled in Orcaflex, and we couple both these subsystem models using the application programming interface. Now let's look at what happens in the Simulation X part of the model. We see that initially the winch is unwound, the winch drum is turning, and the load is being lowered. And as the simulation progresses, the load is lowered to a depth and then raised out. So this shows the raising of the load. We notice that the direction of rotation of the winch has reversed. The red line shows the torque acting on the winch drum, while the green line shows the vertical load acting on the winch wire. We couple the loads to the Orcaflex model, where we see a corresponding response from the load. The load is first lowered. I'll just speed up the simulation. So the load is first lowered and then raised out. And in this simulation, the motion of the load is governed by the response of the winch, which was modeled in Simulation X. So that means we now have results pertaining to both the hydraulic system of the winch as well as the behavior of the winch wire and the vessel, which is modeled in Orcaflex. And this is the advantage of using the Cosimulation methodology. Had we used only Orcaflex, then we would have to specify the rate of the payout rate of the winch wire without actually modeling the hydraulic system of the winch, and so we would not have any results pertaining to that. But using the Cosimulation methodology, we are now able to analyze the response of the drive of the winch. For example, this shows the pressures, the hydraulic pressures in the lines. And the results are discussed in detail in a paper which was presented at the ICANO conference at CUSAT. Another example case for the Cosimulation methodology is in the analysis of top tensioned drilling risers. So the figure shows a semi-submersible drilling rig. The drill string passes through the drilling riser into the wellhead. And as the drilling progresses, the platform responds to the environmental loads. And had the riser not been tensioned by using these tensioning cylinders, what would have happened was that when the platform moved down, if the top end of the riser was fixed, then the riser would buckle. And if the platform moved up, with the top end being fixed to the platform, then excessive tension would be applied to the wellhead and the wellhead would be damaged. So that is why we use tensioning cylinders to hold the drilling riser in a constant, near constant tension. And the arrangement for the tensioner cylinders is shown in this figure, where there are two systems that are generally used. One is called the direct acting tensioner, where the hydraulic fluid is fed into one side of the tensioning cylinder, which is attached to the tension ring on the riser. And in the other case, we again have a hydraulic cylinder arrangement, but it's not directly attached to the tension ring. Instead, we use a wire rope to attach it to the tension ring. And the principle of operation is that since the volume of the high pressure vessels are very huge compared to the volume of the accumulator, any change in the volume of the accumulator will not translate to a significant change in the pressure of the system, and so a near constant tension is always applied to the top of the riser. Now, the system also has an anti-recoil valve arrangement. Sometimes in case of emergency, the riser has to be disconnected from the wellhead for the platform to move away. And in such cases, as the riser is disconnected, the stored elastic energy in the riser causes the riser to recoil. And there are chances that the top end of the riser will then hit the drill floor. And to prevent that, to prevent the riser accelerating upwards, we use something called an anti-recoil valve, which basically throttles the flow so that the upward motion of the riser is happening in a controlled manner. And in the conventional approaches to drilling riser analysis, the tensioner cylinders are usually modeled using spring damper elements in software like Orcaflex and Reflex. We also have another methodology where the entire system is modeled as a spring mass damper system with the riser tensioner tension and the damping of due to the recoil valve being modeled in the spring mass model. And earlier in 2010, Ronnie Sten, who was one of my PhD co-supervisors, he used Simulation X to formulate a parametric model of the DAT cylinder, and then he used that parametric model to specify the spring damper model of the tensioner in a software called Reflex, which is a global riser analysis software. And he also proposed the establishment of an integrated model with real-time communication between the riser analysis software and the multiphysics software Simulation X. And so that's how we extend the methodology to the proposed Cosimulation methodology, where we use Python to enable the application programming interface between Orcaflex and Simulation X. So we develop the Simulation X model for the riser tension system, where all the components are modeled, including the pressure vessels and the DAT cylinders and the accumulator and the anti-recoil valve. And we use the API interface to connect it to the Orcaflex model, where we model the semi-submersible drilling rig and the wellhead and the riser connecting the rig to the wellhead. Initially, we present the results for a simplified system, where the platform is a simple catenary moved buoy with a moved pool, through which the riser passes to attach to a hydropneumatic cylinder, which represents the tensioner cylinder. The hydropneumatic system is modeled in Simulation X, and the platform and the riser is modeled in Orcaflex. And we use the API interface to interface these two subsystems. We present the results in a paper which has been accepted to a journal. Now let's take a look at the simulation. So initially the riser is in the connected condition and the system is responding to the waves. In the third cycle, the riser is going to be disconnected. So in the next cycle, it's going to be disconnected. As it is disconnected, the DAT cylinder retracts and the top end of the riser hits the DAT cylinder. And again, the system continues to respond to the waves. So what happens is that initially in the connected condition, since we have specified the wave heights to be quite high, as the buoy rides the wave crest, the dat cylinder is fully extended and the piston of the dat cylinder actually hits the gland end of the cylinder. This is shown by the simulation X results, where if you look at the cylinder force, we see this sudden compressive force on the gland end of the cylinder. And corresponding to that, if you look at the Orcaflex results, the effective tension on the top end of the riser is seen to spike as the cylinder hits the gland end. As the riser is disconnected at 20 seconds, the stroke of the cylinder begins to reduce and it goes to 0. This means that the piston is now hitting the top end of the cylinder, and it rebounds a few times and then comes to rest at the 0 stroke. A corresponding response of the LMRP can be observed from the Orcaflex results. Initially, as the cylinder retracts, the LMRP is raised, but due to the downward motion of the platform coupled to the rebound of the piston in the dat cylinder, we see that the LMRP drops down, and after the few rebounds, it then begins to respond to the wave along with the buoy motion. We can also see what happens when the piston hits the top end. We see that again the top end goes into compression, and we see a corresponding response in the effective tension at the top end of the riser, where the negative stresses means compression. And so this is the advantage of the Cosimulation methodology, where we can get results from both the multiphysics software as well as the ocean engineering software. Having successfully simulated for the simplified system, we extend the methodology to a full-scale system where we model the entire riser tension system in Simulation X, and we model the semi-sub drilling platform along with the riser in Orcaflex, and we present the simulation results. Let's have a look at the simulation. So initially the riser is in the connected condition and the platform is responding to the waves. The platform will begin to pull away from the wellhead in the next cycle, and the riser will be disconnected. So now the platform is pulling away and the riser is disconnected. As the riser is disconnected, it starts moving up, but you observe that in this case the acceleration is brought down due to the presence of the anti-recoil valve. As after the platform has moved away to a safe location, the riser is then lowered to what is called as the hang-off configuration. So after this, again the platform begins to respond to the environmental loads in its new position with the riser in the hang-off mode. And we will just wait for the simulation to end. And again, the results corresponding to the response of the riser tension system as well as the platform motion is presented. This work is in progress, and it is being made ready for submission to publication. So that brings us towards the close of this presentation. We'll briefly recap what we did. In the introduction section, we defined what a multiphysical simulation is and what a mathematical model is. We then looked at the analogy between the spring mass damper system and a floating object. We looked at why frequency domain hydrodynamic analysis is required, and we looked at the wave body interaction problem. We then looked at the simplifications that can be applied in case of non-diffracting objects. We then talked about using the convolution technique for time domain simulation using frequency domain parameters. We then looked at why we need multiphysical simulations and discussed the limitations of conventional ocean engineering simulations. We then introduced Modelica as a language for the modeling of ocean engineering systems. And we also briefly looked at what the cosimulation methodology does. We then discussed the development of Modelica component models for regular waves, irregular waves, depth-varying current, non-diffracting floating objects, and quasi-static catenary moorings. We then grouped together all these component models to develop the Modelica Ocean Engineering Library, and we discussed the whole process in 3 publications. As a design tool, we discussed the work done by researchers at Manhattan College, where they used the Ocean Engineering Library to design a navigational buoy. We then talked about extending the capabilities of the Ocean Engineering Library by developing component models for mooring using the lumped mass approach, by developing component models for diffracting floating objects, where we discussed the publication regarding OM-HYDE, the frequency domain hydrodynamic analysis software. We then talked about the cosimulation methodology for offshore load handling. And finally, we talked about the cosimulation methodology for top tension risers. I often get asked how one begins out with Modelica and OM-Edit. So the best way is to first download and install OM-Edit on your system. Then learn the basics of simulation using OM-Edit, using the spoken tutorials from IIT Bombay, for example. Explore the Modelica language, and you can use resources like the website Modelica by Example by Dr. Michael Tiller, who is a Modelica expert. And once you're comfortable with the Modelica language, you can get initiated into the Ocean Engineering Library. The first step is to read the publication towards the development of an Ocean Engineering Library for Open Modelica. Then download and install the Ocean Engineering Library to your OM-Edit. The download location is given inside this paper. Then read the publications, Modelica component model for oceanic surface waves and depth varying current, and Modelica component models for non-diffracting floating objects and quasi-static catenary moorings, followed by the articles on the dynamic simulation of a mooring catenary based on the lumped mass approach, and simulating the dynamics of a chain suspended subsea load using modified components from the Modelica multi-body library. Then start experimenting with the Ocean Engineering Library and try developing your own component models, and that is the best way to learn not only ocean engineering but any domain of engineering. You can simulate the system response using Modelica, and that deepens your understanding of the underlying concepts once you start analyzing the system response and what different change in inputs does to your outputs. You can really gain an intuition on how the system behaves. And so finally I come to the concluding slide of my conclusion, where I leave the viewers with the following statement. Multiphysical models are the only way to understand how a yet to be built system would behave, and they seem to be the only way to evaluate pioneer engineering endeavors. Of course, techniques like data-driven modeling and machine learning approaches go hand in hand with first principles models, like we do in Modelica. But to generate the data sets required to implement a machine learning algorithm, you again need to run simulations if it is an yet to be built system, and these simulations would have to be based on first principles modeling. I leave the interpretation of the last slide to the imagination of the viewers, and thank you. If you have any questions, we can discuss that now.